Looks like it's just about time to go. I'm actually grading a student's test right now, looking at all their work. So, trying to knock this out so I can be ready to roll when that happens. Yep, this looks all good. All right, so last time we started, our last time we met, we were working on chapter 9, and I had just gotten through example 9.3, which is a conservation of momentum problem where you had a train car moving at 8 meters per second, runs into a sitting still train car, it sticks together. And they asked what was the speed of the two after they collided and stuck together in what we call an inelastic collision or a perfectly inelastic collision. Anytime two things run into each other and stick together, that's called a perfectly inelastic collision. And as I said, in a frame of reference that we call the center of mass frame, the one where the total momentum before the collision is zero, in that frame, all of the kinetic energy is completely lost. So that's why they call it totally inelastic, whereas inelastic means kinetic energy is conserved. So we're going to start off from there, even though you're my only student that's here, and that's fine. No students have to be here, but like I said, feel free to ask me any questions you want, and don't feel particularly bad about doing it since you're the only student. That's even more the reason to do it. So, do you have any questions before I get started, other than the question you asked about the test, Christine?
No, I'm good.
Okay, no problem. I will grade yours next, right after we finish with class, so that way you'll have your grade immediately after this. Okay. Did you
Okay.
did you email me your work, by the way?
I did,
Okay,
yes.
so far I've hit five, six students in a row, and they all their pictures were good enough where I haven't even had to use their work that they sent me. So hopefully that continues because that makes my grading a lot faster. It's a very slow process otherwise. I'm going to go ahead and share my screen, and that's my iPad screen. And I've already got the information written out for the first problem that we're attempting to do, and that problem, oops, I don't know if I did that. Nope, I did not do that. Oops, there it is. Okay. And that problem we're doing is example 9.4, where a rifle is being fired and you're asked to calculate the recoil speed. So if you've ever shot a gun, especially a rifle or a shotgun or something like that, you'll know that when you fire, you feel a little kickback like this. Of course, if you do a handgun, especially a higher caliber handgun, you'll feel some kickback too. What's really going on there is initially the gun and the bullet are all in one location and they're not moving at all. So when you actually first look at the system, which I'm calling the system, the bullet plus the gun, and when you look at that system, they're not moving initially, so the initial momentum is zero. Then after the trigger is pulled, an explosion occurs in the cartridge, and that forces the shell out of the cartridge. And that also, that same explosive force that pushes the shell forward with the muzzle velocity V sub M is the same force that's pushing backwards on the gun. And that force causes the gun to move back with some initial velocity, and that velocity is called the recoil velocity. And you're sort of imagining it as if you didn't have any kind of shoulder or anything stopping it with this conservation of momentum problem. So it gives you an idea of if you would sort of set this gun up on some like very frictionless roller skates or something and had a remote control device that could pull the trigger, then it's how quickly that very, very light roller skate would allow the rifle or the gun or whatever type to roll backwards. So that's really what we're calculating. And example 9.4, it says calculate the recoil velocity of a 5 kilogram rifle that shoots a 0.20 kilogram bullet at a speed of 620 meters per second. And that's the speed we call the muzzle velocity. And you can look that up on any, if you actually purchase a gun, it'll have a manual, and the manual usually tells you what the muzzle velocities are for each of the models and that sort of thing. So that's what we're using here. I've got this written up, and you can see example 9.4. I'm showing the big M is the mass of the rifle. The little m is the mass of the shell of the actual bullet, not the shell, and Vm is the muzzle velocity. And what we're looking at in the left-hand side is the two sitting perfectly still, and then the right-hand side, you're just seeing the barrel of the gun, and I'm showing that that barrel is moving to the left with some V recoil, and the bullet is moving to the right at 620 meters per second. So now I'm going to show you how to conserve momentum. Solution. requires P initial is equal to P final. And this is technically a vector equation, but we're talking one-dimensional motion here. So really the vectorness is handled by a positive or negative sign. Positive signs point in the direction of positive coordinates, which I'm going to assume is pointing to the right. And then negative sign means it's pointing in the negative direction, which would be to the left. I'm also going to use the fact that P is equal to mass times velocity. Again, that's a vector equation. But P initial is equal to m times 0 plus little m times 0, which equals 0. And that's just because the rifle and the bullet are both sitting perfectly still. After the uh, after the explosion or the firing of the gun, you've got m, which is 5.0 kilograms times v recoil plus little m, which is 0.020 kilograms times 620 meters per second, and that's the final momentum. So we can set P initial equal to P final, and then we'll have 0 is equal to 5.0 kilograms times V recoil. Plus, now if I multiply this by zero point zero 0.02, basically I can take the 620 and divide it by 100, which would be 6.2, and then multiply that by 2, be 12.4. So this is going to be 12.4 kilograms meters per second, and therefore we can solve for V recoil, and V recoil is going to be negative. In this case, it's going to be 12.4 kilograms meters per second divided by 5.0 kilograms. So we get V recoil is equal to 5 goes into 12 two times, 2.4 is left over. 2.4 is almost a half of 5. So we're going to say this is roughly 2.4 something, 2.5 maybe. And in fact, if you compute it, it's about 2.5 meters per second is the final velocity. And the negative shows us that it did, in fact, go in the opposite direction of the 620, which we consider to be positive. So the way I drew it is the 620 is going to the right, and I called that a positive number. And the fact that this came out negative is consistent with that. Any questions on that one?
What equation did you use for that P final?
Okay, for basically momentum for a single object is m times v. But what I mentioned when we first covered momentum is you don't have to apply Newton's second law, for instance, just to a single object. You can take all the objects, like I mentioned a flock of birds, and if you wanted to calculate the total momentum of the flock of birds, treating the birds as a system, it'd be m1 times v1, where m1 is the mass of the first bird and v1 is velocity of the first bird, plus m2 v2 plus m3 v3, and all of that. So when you actually go to calculate momentum, you take all the parts that you're calling the system. And in this case, I chose to call the system the rifle plus the bullet. Does that make sense?
Okay, okay.
So yeah, it's just M1 V1 plus M2 V2. Of course, if you had more than that, you'd add more terms, but that's all the terms we had in this case. That's a good question. It's definitely something you got to think about, and it's sometimes it's a little bit tricky figuring out exactly what's the best system to use. Just remember that when you apply Newton's second law, anything inside of the system, you can't calculate the forces on them from other parts of inside the system. So if I wanted to calculate the force on the shell as a result of the rifle, I couldn't do that because I treated the shell and rifle as one system. But if I did F equals MA or F equals dPdt for the shell, and then I did another F equals dPdt for the bullet, then I could use that to figure out what the actual force on the bullet and stuff like that was. So that's the big problem with that. Now, conceptual example 9.5, I usually don't necessarily write out anything with this, but I wanted to explain it. So it says conceptual 9.5. Sorry, the yawns are coming back. Falling on or off a sled. An empty sled is sliding on a frictionless ice when Jeannie drops vertically from a tree down onto the sled. When she lands, does the sled speed up, slow down, or keep the same speed? So in this case, we have a sled sort of moving by horizontally, and we have Jeannie sitting up here in a tree. And as the sled moves by, she drops straight down. And since she's dropping straight down, that means she's not moving forward the same direction as the sled, nor moving backwards the opposite direction of the sled. She's moving straight down. Now, she would intend to actually make the momentum of the sled move in the downward direction. In other words, her hitting that sled has the potential to make the sled move down, but the earth is pretty tough, so the earth doesn't really give way that way. So what ultimately happens is basically she hits the sled, and then the normal force on the sled increases for that split second while she's hitting it and coming to a stop. But the main thing is Jeannie doesn't have any velocity in the same direction as the sled, the opposite direction of the sled, or to the right of the sled, or to the left of the sled. She did have some down of the sled, but that force was able to match that. So in this case, the total momentum beforehand has got to equal the total momentum afterhand. And the total momentum beforehand was just the mass of the sled times the sled speed. After that, though, now the sled is not the only part of the system moving. Now both the sled and Genie are moving. So what you have, and actually this will be helpful for me to write, so I'll go ahead and write it in this case. So this is example. Ah, man, I hate it when it does that. This is example 9.5. So what we have is Genie falling down like this, and a sled going by like this with some velocity. So the initial momentum, P initial, is basically just the mass of the sled times the velocity of the sled. That's the initial momentum. Uh, and Genie, of course, is sitting perfectly still. Then, after Genie lands on the sled, okay, she's a little sort of bump like there. Okay, the momentum after this would be the mass of the sled plus the mass of Genie times the new velocity of the system. So I'm just going to call that V2. Now, what you see is ms times v, the initial velocity that the sled had, is going to be equal to from PF equals or PI equals PF. That's going to give us the mass of the sled times the initial velocity of the sled is equal to the mass of the sled plus the mass of Genie times the new velocity. And you can see that that new velocity, V2, is going to be the mass of the sled divided by the mass of the sled plus the mass of Genie times the initial velocity of the sled. So you can see in this case, in part A, when she falls down on it, she is actually going to cause the sled to slow down, so it will actually slow down. Now, if you want to think of this in terms other than momentum, because maybe you better understood Newton's second law than you did this Newton's second law with momentum, then imagine this. When Jeannie's falling down, not only is she going to feel a force upward from the sled pushing up on her when she hits it, but she's also going to feel a force of the sled pushing forward on her because the sled's attempting to just keep moving forward, forward, forward. And when she hits it, it's going to move her along with the sled. And maybe, if the sled's not going fast enough, she might bring it almost completely to a stop. Who knows? But the main thing is the sled is applying a force to Jeannie, and that's going to cause Jeannie to speed up to whatever speed the sled has because the sled doesn't have any choice. Once it starts pushing her, her friction is going to be sufficient to hold to the sled. So the sled is just going to continue to move with whatever that new velocity is. So that's the answer to part A. Part B, it says later, Jeannie falls sideways off the sled. When she drops off, does the sled speed up, slow down, or keep the same speed? This is sort of the reverse of what just happened in that she's now leaving the sled with a velocity that's perpendicular to the velocity of the sled. So in that sense, it's sort of the reverse because she's leaving the sled instead of entering the sled. But in light of her leaving the sled off to the side, she could, in principle, just roll off and not apply any force to the sled. If that's the case, then the sled's not even going to have any compunction to slide off a little bit to its right if she fell off the left, or a little bit to its left if she fell off the right. That's not going to happen at all if she doesn't apply a force to it. And that's sort of what we're going to assume here. So, assuming she just sort of rolls off without actually applying a force to the sled, then what's going to happen is she's going to hit the ice. And if the ice is pretty frictionless, then she's going to continue to move at the same velocity that her and the sled had after she rolls off. Just she'll be doing it beside the sled instead of on the sled. And the sled is going to continue moving with that same velocity as well. So in that case, they don't slow down or speed up in part B. Any questions on that? Okay, so it looks like y'all got that. All right, we're going to move on to the next section, which is about collision and impulse. And part of what I did when I first introduced chapter 9 was I did let you know that impulse is really the change in momentum, the delta p. And the delta p can be equal to delta p equals the integral of dp from p initial to p final. But because Newton's second law says F equals delta P over delta P is also equal to the integral of F, the net external force, times dt. So impulse is both of those things, the integral of the net force time over time. So an area under the curve, basically, of a total force versus time diagram is impulse, but also change in momentum is impulse. So we keep that in mind. And now we're going to go ahead and work a problem. In this case, let's say we're doing example 9.6. So example 9.6 says, estimate the impulse and average force delivered by a karate blow that breaks a board a few centimeters thick. Assume the hand moves roughly at 10 meters per second when it hits the board. So I'm going to say V0 is equal to 10 meters per second. I'm going to say the mass of the hand, so I'll just write it as M sub H. I'm going to say that is about 1.0 kilograms. Remember, a kilogram is about 2.2 pounds, so that seems kind of reasonable for most people's hands. Obviously, some people have much smaller hands. But what we're going to picture here is that basically this hand is coming down, it's going to hit this board, and we're trying to imagine what's the sort of minimum force that you could use to break it. And the minimum force is a force that's going to allow it to hit it at its initial velocity, and to bring the board will completely bring the hand to a stop as it gets just barely to the thickness of the board. So I'm going to call delta x the thickness of the board. I'm going to call that 2.0 centimeters. Your book calls that 1 centimeter, but that doesn't seem reasonable to me. That could be because your book is assuming that all the acceleration from velocity of the hand being 10 meters per second to the velocity of the hand being 0 meters per second. They might be assuming maybe that happens in the first half of the thickness of the board if the board was 2 centimeters. But either way, I'm going with 2 centimeters instead of 1 centimeter. Okay. And what they're asking, as I said, is estimate the impulse. So J equals delta P equals question mark, and the average force, which would be F average, is equal to question mark. That's what we're shooting for. Solution. What we're working on here again is momentum P is equal to M times V. And remember, when you're talking about a system, that could be P total is equal to M1 V1 plus M2 V2 plus M3 V3. But right here, we're not talking about any of that. That's momentum. We also know that the summation of the forces is equal to dP dt. And we also know that that can become J is equal to the integral of the summation of the forces dt from T1 to T2. but because of the equation being an equation, it's equal to the other side, and therefore that's also equal to the integral from P initial to P final of dP, like that. And that is the two different ways that we're looking at it here. And now I'm also going to make use of a kinematic equation. I'm actually going to use a kinematic equation that we're not that we don't use that often. Specifically, if A equals a constant, and now that's a big if, but it's an if that we can do just to get our foot in the door. So we can make the estimate that the acceleration of the hand when it's hitting the board is a constant acceleration. And it's such a small time interval, I'm not sure we would sift out much of a difference in the acceleration being a constant versus not being a constant. So it's not that big a deal. But either way, if we use it, assuming it's a constant, then we're open to using the kinematic equations that we derived. And if A is a constant, then we know that V bar is equal to V0 plus V1 or plus V1 over 2. That's a pretty normally obscure equation that we'd use, but it is one that comes in kind of handy in this type of case. Okay. So first off, we want to calculate the change in momentum, and the change in momentum, delta P, is equal to mv final minus mv initial. And this is one dimensional, so that's why I just dropped the symbols here. We're talking about, in this case, the actual momentum change of the hand, and the momentum change of the hand is going to be a result of the force that the board applies to the hand, and of course, that's going to be equal in magnitude but opposite in direction to the force that the hand applies to the board. So we'll still get the right answer in magnitude. We'll just be working for the other thing. So with this in mind, we're going to say this is equal to 1.0 kilograms. And rather than write the mass twice, I'm just going to factor that out and say the final velocity is going to be 0 meters per second because I'm imagining the hand hitting the top at that instant. It's going 10 meters per second. And then as it reaches the bottom of or as it goes a whole 2 centimeters of thickness of the board, it's going to reach a velocity of 0 meters per second. So that's why I wrote the final velocity 0 meters per second and the initial velocity is 10 meters per second. And therefore, we get specifically that 1.0 kilograms times 10 meters per second is negative. And actually, that's supposed to be a negative between there. I don't know why I put a positive or a plus in there, but like that. So this is negative 10 kilograms meters per second is the change in momentum, and therefore that is J. So J, in this case, it said estimate the impulse and the average force delivered by a karate blow. Now, the karate blow is actually putting a force in the positive direction, not in the negative direction. So we might be better served by saying the impulse is positive 10 kilograms meters per second, like that. So that's the first part of the question. Now, the second part of the question is if you're taking the summation of the forces is equal to dp/dt, I think you'd agree that the largest, most significant force acting on this board should be the force that the hand is applying to the board. And in fact, when the hand applies it to the board, that's going to be a sort of big force. Obviously, for it to stay on those cinder blocks as it looks like it is in this diagram, then those two forces on the left and right have to add up to give you that force. But that's not the force that's causing the change in momentum. So we're focused on the force that the hand is applying. And with that in mind, we're going to say that F on average, and I'm saying it's now the average F instead of the sum of the forces because I just argued that the major force is only the force of the hand, but that is going to be equal to J over delta T because J is delta P. Okay, I could have written this delta P over delta T, but then, well, I'll go ahead and show you. So this could be delta P over delta T, but delta P is J. So because of that, we can write 10 kilogram meters per second. And again, I'm just taking the magnitude because the force that the board applies is actually in the upward direction, which we're probably going to call the negative direction. That's why we got the negative impulse. But we're talking about the other force, the force that is delivered to the board. So we're going to use that. But in order to do it, I got to find out how much time it takes to actually make it through the board. In other words, how long is the hand contacting the board so I can deliver that force? Well, that's where I'm going to use the average velocity. We can say the average velocity is equal to basically distance delta x over delta t. So that means delta t is actually going to be equal to delta x over v bar. And v bar from the equation we just told you is going to be, let's add 0 meters per second for v0 plus 10 meters per second for V2 or V1, and then all of that is divided by 2, so that gives us 5.0 meters per second for the V average. So what I'm going to do now is take 2.0 times 10 to the negative 2 meters and divide that by 5.0 meters per second. So now I've been able to compute what the F average is. So I'm basically going to end up multiplying the 10 times 50, times 5 to make 50. And then I'm going to multiply that by 10 to the 2. That'll make it 5,000. And then I'm going to divide that by 2. So that's going to be 2,500 newtons is the average force. So that's how we do that. Anybody have any questions on that one? Your book actually did 5,000, but again, that's because they got their result by assuming that the change in velocity of the hand is only going to happen over a 1 centimeter distance. I was saying it's probably going to happen over a 2 centimeter distance, and that makes the requirements of the force a little bit less severe. So that's why you could probably do it with 2,500 newtons instead of 5,000 newtons like your book has given you. Any questions on that? All right. So next we need to talk about conservation of energy and momentum and collisions. So I want to give you a little rundown on that real quick. So what we're imagining here is basically we're going to start off with looking at one-dimensional collisions. So what you might think of, for instance, is a mass m sub a moving with a velocity v sub a runs into a mass m sub b moving with a velocity v sub b, and the velocity could actually be the other way, by the way. We could just make sure, for instance, va is bigger than vb, so it'll bang it from behind or whatever. But the main thing is we have some velocities, and if it comes out negative, then that'll be say meaning we're moving to the left. If it comes out positive, we're going to say it's moving to the right. A short time thereafter, you're going to find that the two balls collide, and with that you get some excitement. Pew, pew, pew. And it's not physically possible for me to draw that without making pew, pew, pew noises because I am still in like third grade. But after the collision, what's going to happen is now the blue ball is going to be moving to the left, and it's going to have a velocity va prime, and the red ball would probably be moving to the right, and it's going to have a velocity of VB prime. That's the symbols that we're going to use throughout this, including in the two-dimensional collisions as well, instead of just the one-dimensional. So we're going to say the collisions or the velocities before the collision was just A and B, but the velocity after the collision was A prime and B prime. So that's what we have. Now, conservation of momentum would say the following. We've got P initial is equal to MAVA plus MBVB. And of course, if we were actually dealing with two dimensions, we'd have to write vector notation and, take sines and cosines to find the x components and the y components and that sort of thing. But in one dimension, this will all be covered by numbers and plus or minus signs. So there's the initial potential, or excuse me, the initial momentum. The final momentum, P final, is going to be MAVA prime plus MBVB prime like this. Therefore, conservation of momentum is this. That's equal to MAVA plus MBVB is equal to MAVA prime plus MBVB prime. That is our equation, at least in one dimension, for conservation of momentum. If the collision happens to be elastic, then that means kinetic energy is conserved. So if the collision is elastic, then K equals a constant. Now, do y'all recall by any chance, and by all means, type this in the chat if you know the answer, or just blurt it out if you know the answer, but do you know under what conditions momentum is conserved? Okay, remember what we came up with that from? It was Newton's second law, the way Newton gave us, which says the summation of forces is equal to dp dt. If the net force acting on the system is zero, then the summation of forces is equal to zero. So you have zero equals dp dt. And the only way you can have a derivative equal to zero is if the thing that you're taking the derivative of is a constant, and that means the momentum is a constant. And that's exactly what we're doing when we say P initial equals P final. We're saying P is a constant. So the conditions under which momentum is conserved is when the net external force acting on the system is zero. That doesn't have anything to do with any forces that one part of the system might be applying to another. Like when this collision happens, mass A is going to apply a force to mass B, and mass B is going to apply a force to mass A. But that doesn't matter at all because those are internal forces. The system is mass A and mass B, so anything that happens between them is an internal force. And not only that, because you did it that way, you can't even tell what those forces are. Okay. All right. So now, when the kinetic energy is conserved, we call that an elastic collision, and that would be explained by this. We would have 1 half m sub a v sub a squared plus 1 half m sub b v sub b squared is equal to 1 half m sub a v sub a prime squared plus 1 half m sub b v sub b prime squared. And notice how I made a point to write the 2 way up above the prime so it didn't like an exponent of 12. But that is our equation for conservation of kinetic energy, at least for a two-particle collision. Kinetic energy before the collision total is equal to the kinetic energy after the collision total. Any questions on that? All right, so that's the two conditions we're going to use, and we'll generalize that to higher dimensions later. But right now, we're going to apply this, and I'm going to show you a neat little trick that allows us to figure out something about one-dimensional head-on collisions that are elastic. Okay, so I'm going to take these equations. Let's write them up here. Let's say uh, head-on. Oops. Head-on 1D elastic collisions. And I just got a whole hodgepodge of things capitalized and not capitalized. I don't even know what's going on there. But anyways, okay. What we're going to start off with is M sub A V sub A plus M sub B V sub B is equal to M sub A V sub A prime plus M sub B V sub B prime. That's conservation of momentum. That's going to be equation 1. And now I'm going to take conservation of kinetic energy, 1 half m sub a v sub a squared plus 1 half m sub b v sub b squared is equal to 1 half m sub a v sub a prime squared plus 1 half m sub b v sub b prime squared. That's going to be equation 2. Now, here's the trick. So this is something that I find it much easier just to derive it every time if I can't remember it. So please hear me out in the way I'm going to tell you to derive this because that's a really valuable skill, something you should learn anyways, and it'll be helpful to you. That being said, you can just use the result, and that's fine as well. So I'm going to first take equation 1 and get all the A data on one side and all the B data on the other. So actually, first in equation 1, get all A's on one side and B's on the other. So when I do that, what I end up getting is MAVA minus MAVA prime is equal to MBVB prime minus MBVB, like that. And in fact, we can write it a little better. We can say MA times VA minus VA prime is equal to MB times VB prime minus VB. Okay, I'm going to call this equation 1 prime because it looks like equation 1. It came from equation 1, and it's only moderately different in that I solved for something different. Okay, now, second, multiply 2 by 2, and then get A's on one side and B's on the other. So multiplying by 2 gets rid of all the 1/2. That's the main thing I'm doing there. And what I'm going to get then is MA VA squared minus VA prime squared is equal to MB VB prime squared minus VB squared, like that. That's going to be equation 2 prime. Now I'm going to divide 2 prime by 1 prime after factoring 2 prime. So difference of squares, we know how to factor that. It's for instance, VA squared minus VA prime squared would be VA minus VA prime parentheses again VA plus VA prime. So what we're going to do is say MA VA minus VA prime times VA plus VA prime is equal to MB VB prime minus VB times VB prime plus VB. So now I've factored equation 2 prime like I said I would, and now I'm going to take that and divide into it equation 1 prime, which is MA times VA minus VA prime, and that's equal to MB times VB prime minus VB. So you can see that when I divide these two, This MA cancels out with this MA. This MB cancels out with this MB. This VA minus VA prime cancels out with this one. And this one cancels out with this one. And all I'm left with is VA plus, oops, let me go back to green. All I'm left with is VA plus VA prime is equal to VB plus VB prime, like that. And that's not necessarily the best way to write it. I'm going to get rid of the A's being on one side and the B's being on the other. I want to have everything from before the collision on the left and everything after the collision on the right. And with that, I end up getting VA minus VB, so A minus B in other words, is equal to the negative of VA prime minus VB prime. So I skipped a couple steps, but I think y'all can follow what I did there. But this is a wonderful happenstance. It turns out what it's saying is the difference of velocities before and after the collision in a elastic collision in which momentum is conserved and it's 1D head on reverses the sign of the difference in velocity. So the difference in velocity before the collision is equal to the negative of the difference in velocities after the collision. And that just makes one equation that we can use instead of starting with equation one, conservation of momentum, and equation two, conservation of kinetic energy. We can start with this, and that sort of is already taken into account both of them. And then we can use any of the other ones that we want to help us figure out the rest. That'll make more sense once you see an example. But does anybody have any questions on that? Okay, so let's look at example 9.7. Example 9.7 says a billiard ball of mass m moving with speed VA collides head on with ball B of equal mass. What are the speeds of the two balls after the collision, assuming it is elastic? Assume A, both balls are initially moving are moving initially VA and VB, and B, ball B is initially at rest. So that's the two types of problems we're going to deal with. We're going to say M is equal to MA is equal to MB. So basically, what that means is in the equation, I had MAVA plus MBVB equals MAVA prime plus MBVB prime. I can just cancel out all the M's. And the same thing's true in the 1/2 MAVA squared, blah, blah, blah. All the M's drop out as well as the 2. So we can make use of all that. In part A, we want to know VA prime equals or excuse me, VA prime equals question mark, VB prime equals question mark, and we're assuming we know VA and VB. And then in part B, we want to know VA prime equals question mark, VB prime equals question mark, and VA is something, but VB is actually equal to 0. So that's what we're shooting for here. Solution. One thing we know is what we just discovered, and that is the difference in velocities before the collision, VA minus VB, is equal to the negative of the change of the difference in velocities after the collision. So it's going to be minus VA prime minus VB prime. And then, of course, we can still use M. Well, in this case, we get rid of all the M's. We're just going to use VA plus VB is equal to VA prime plus VB prime. Notice this is equation one with the mass canceled out. Okay, that's all that is right there. We could also use, of course, the equation for VA squared plus VB squared is equal to VA prime squared plus VB prime squared. We can use that as well. But that's the total that we're shooting for. So how do we go about doing this? Well, the first thing I'm going to do is I am going to plug, let's say solve, I'm going to call this equation 1, I'm going to call this equation 2, and I'm going to call this equation 3. Solve 1 for And what I want to do is solve for one of the variables that I want to know. I just got worse, which is, let's say, VB prime. So solve one for VB prime. So we have VA minus VB is equal to, I'm going to distribute that negative so it helps us out a little bit, minus VA prime plus VB prime, which means VB prime is equal to VA minus VB plus VA prime, like that. Now I can plug that into 2. I'm going to call this 1 prime and plug 1 prime into 2. So when I do that, I'm going to get VA plus VB is equal to VA prime. Oops. Now this is supposed to be plus VB prime, but I just found out that VB prime is VA minus VB uh, plus VA prime. So you can see in this case, I'm getting a VA and a VA that cancels out on both sides. That VA cancels out with this VA. And I get a 2 VB prime and 2 VA prime and 2 VB. So from this, I can pull the VBs on the left and I'll get 2 VB is equal to 2 VA prime. And what that means is VA prime is equal to VB. So what happened was the moving particle, the initial particle A was moving towards particle B. It hits particle B, or billiard ball B, and billiard ball B immediately takes off with the same speed that A has at the end. So that's sort of what we're looking at is the velocity of the initial A ball is going to become the initial velocity that B had. And you might suspect that the velocity that B will be the velocity that A had, and that's going to work out. So that's one way you could do it. Another way we could have done it is we could have just added equations 1 and equation 2. I did it a different way. Your book did it that other way. But this time, let's subtract equation 1 from equation 2. So subtract, oops, let's say subtract 1 from 2. So if I subtract 1 from 2, what I'm talking about here is VA plus VB equals VA prime plus VB prime, and I'm subtracting from it. Uh, Now remember when you subtract that you've got to distribute that negative. So for instance, I'm taking the left-hand side of V of equation 1, which is VA minus VB, and I've got to distribute that all over the whole thing here. So I'll take out these parentheses for right now and just put a big square bracket around here because otherwise we're going to have a bunch of brackets. And then this is minus VA prime minus VB prime, like that. So when I distribute that negative, what we're going to get is the left-hand side is VA plus VB minus VA, and then minus minus would be plus VB. And the right hand side is going to become VA prime plus VB prime. And then I've got minus a minus because the minus was already in front, and then I'm doing a minus for subtraction. So that's just going to make plus VA prime minus VB prime. In this case, it looks like the VB prime is disappearing and the VA is disappearing. So it looks like we're going to get the same expression. So I shouldn't have subtracted that one. Maybe I should try adding them. So this gave the same result. So try adding. Do y'all see what I mean when I said it gave the same result? Basically, I was still getting uh, VA, VB is equal to VA prime. So that doesn't help me. So now I'm going to try adding them. And it's a little easier to add them. You look at the left-hand side and the left-hand side, forget about the negatives. I get left-hand side is VA plus VB of equation 1. And then plus equation 2 would be plus VA minus VB. And then the right hand side has VA prime plus VB prime. That's from equation 1. But now I'm going to add to it negative VA prime and positive VB prime. So in this case, you see I've got a, dang it, looks like everything else is canceling out again. It looks like a VA and a VA gives me 2 VA, a VB and a VB gives me nothing. So 2 VA is equal to the VBs are, okay, this is working out all right. The VA and the VA prime cancel out, but I get 2 VB prime. So in this case, I can say that VB prime is actually equal to VA, which is what I argued was going to happen. Basically, I said that it's like they're going to trade velocities, and that's basically what happens. Ball A comes in, hits ball B, and ball B leaves with the velocity that A had, and A leaves with the velocity that B had. Okay, so that's all for part A. Now for part B, we want to consider when the velocity of B is zero. So I'm going to go as follows. So our equations are now VA minus VB is equal to negative VA prime minus VB prime. But in this case, VB is supposed to be equal to zero. So I'm just going to erase it like that. So I'm going to call this equation 1. And then VA plus VB equals VA prime plus VB prime. But VB is supposed to be equal to 0, so I'm going to erase that. And this is going to be equation 2. So you can see it's got a long space in it, but the main thing is I wanted you to see where it's coming from. So now what I'm going to do is add equation 1 and 2. So the left-hand side is going to give me 2VA because VA plus VA is 2VA. And the right-hand side is going to give me negative VA plus VB. Both of those are prime. Plus VA prime plus VB prime. Like that. And in this case, you see the VAs are canceling out. The VA prime and the negative VA prime cancels out. And in this case, I get VA is actually equal to VB prime, or I'll write it in the opposite order so it makes a little bit more sense. We're actually solving for A prime or B prime, so VB prime is going to be equal to just plain VA. So that is the actual result for the first part. Specifically, we've now found that the particle B, which was a target particle sitting perfectly still, it's going to leave the collision with exactly the same velocity that the initial particle had. This is sort of like, I don't know if you've seen Newton's cradle where they've got little strings and the balls hanging from it, and then right next to it, another string with a ball hanging from it, and another like that, and you pull out two of them and you let them fall down, they hit, and then two of them pop out the other side and swing up, and then two back like that. And if you do one, one will do it. If you do three, even though there's five, it'll do three so that the middle one's moving every time. That's what we're showing here. That's very nearly an elastic collision, and that's something important to understand. Elastic collisions are more likely to be elastic, or collisions are more likely to be elastic if it's two rigid, really hard objects running into each other as opposed to two rubbery balls running into each other. Okay. Now I'm going to try to get the other result, and to do that, I'm going to subtract 2 from 1. So subtract Let's subtract 2 from 1. In this case, I'm going to say, I don't know why I wrote red, but 2 from 1. I'm going to write down the left-hand side of 1 is VA, and then I'm going to subtract from that the left-hand side of equation 2, which is just plain VA. So that's what I get for the left-hand side. The right-hand side, I'm going to get negative VA prime plus VB prime. That's the right-hand side of equation 1. Now I've got to subtract from that the right-hand side of equation 2. So that's going to be minus VA prime minus VB prime like that. You can see that the VB prime cancels out with the negative VB prime, and we end up getting, in fact, 0 is equal to negative VA prime, negative 2 VA prime. So our result is that VA prime is equal to 0. And that's exactly what I was talking about with the Newton's cradle device, in that when you drop one ball, it comes down and rams into this side, but it sits perfectly still, and then one ball pops out the other side. That's exactly what's happening here. Any questions on that? All right, so everybody see how you do that? You're just going to use the VA minus VB equals negative parentheses VA prime minus VB prime, and then usually you'll just use the momentum equation because the other one's got squares. You don't want to mess with that. So let me try another example in hopes that y'all will get a little bit more experience. So this is example 9.8. Example 9.8 says unequal masses target at rest. A very common practical situation is for moving object M sub A to strike a second object M sub B, the target, at rest V sub B equals 0, sort of part B of what we did earlier. Assume the objects have unequal masses and that the collision is elastic and occurs along a line, i.e. a head-on collision. A, derive equations for VB prime and VA prime in terms of the initial velocity VA of mass MA and masses MA and MB. And then B, determine the final velocities if the moving object MA is much, much more massive than the target. And then C, determine the final velocities if the moving object is much less massive than the target. So that's what we're trying to figure out here. Uh, so what we want to get is we can assume we know MA, we can assume we know MB. If you write a symbol like this without an equals next to it, then go on the assumption that that's the symbol that we pretend that we know the answer for. Okay, so I'm pretending I know MA, I'm pretending I know MB. I'm going to pretend I know VA, and I know VB is equal to 0. But in part A, they want me to find VA prime and they want me to find VB prime. And then in part B, they want VA prime and VB prime if specifically MA is much greater than MB. And then C, they want the same thing, VA prime equals question mark, VB prime equals question mark if MB is much greater than MA. So that's what we're shooting for here. And I will work as follows. Solution. We already know that this is a collision that's elastic, and we're assuming the net external force acting on the system is 0 so that the momentum is conserved. That means we have MAVA. Remember, it's plus MBVB, but the VB is 0, is equal to MAVA prime plus MBVB prime, like that. That's going to be equation 1. But we also know, as a result of the derivation we did earlier, that VA minus VB, which is 0, is equal to negative parentheses VA prime minus VB prime, like that. And that's going to be equation 2. Okay. We can also use conservation of kinetic energy and so on and so forth, but we don't necessarily need it. It's been used already to some extent. So what we can do is we can solve one expression, for instance, for VA prime, and then plug it into the other expression. So let's take, for instance, I'm actually trying to look and see what they did. It doesn't really matter. You can just take any one you want. But if I take equation 2 and solve for VA prime, I get VA minus VA prime or equals negative VA prime. This is aggravating. So I'm rewriting equation 2. It's supposed to be VA is equal to negative VA prime plus VB prime. So from that, I can reach the conclusion that VA prime is actually equal to VB prime minus VA. And that works fine. And I'm going to call this equation 2 prime. And now I'm going to plug 2 prime into 1. And doing that, I get MAVA equals MA times VB prime minus VA plus MB VB prime. So that gives me MAVA is equal to MAVB prime minus MAVA plus MB prime. So I'm trying to solve for either VB prime or VA prime. I just eliminated VA prime, so I'm solving for VB prime. That means I should get all the VB prime terms on one side and all the other stuff on the other side. So what I'm going to do is write that the VB prime side will have, notice it's a VB prime times MA and it's a VB prime times MB. So I'm going to say MA plus MB times VB prime. That takes care of this term and this term. And then on the other side, I have MAVA, and then I'm going to add to it MAVA. So this is 2MAVA. That takes care of that term and that term. And now I'm in a position to solve for VB prime. Specifically, VB prime is going to equal 2MA over MA plus MB times VA. Okay. Now you might notice that looks a little bit like the formula from the Atwood machine, and that's something that I use to remind me. Specifically, the tension on the Atwood machine was 2M2 over M1 plus M2 times M1G. So you can see how it sort of looks like it has that 2 times 1 mass over the sum of the masses in this case. So hopefully that'll help you remember it. But it is a result that we can use. And your book specifically, if you look at the end of the chapter, there's a problem number 64, I think. No, 34. Problem 34, where you can do this exact same process without assuming the initial velocity B is zero, VB is zero, and you can get an actual full two-term expression for VB prime and VA prime. I highly recommend you doing that. If you can do problem 34 at the end of chapter 9, you're in a good spot for knowing how to do this algebra and conservation of momentum stuff. Now, I just figured out the velocity B. Now all I need to do is maybe use equation 2 prime to figure out velocity A prime. So now plug VB prime into what we called was 2 prime because that is already solved for VA prime. So to do this, what I'm going to say is VA prime is equal to VB prime minus VA. And of course, VB prime is 2MA over MA plus MB. All of that times VA and then minus VA. Okay. So with this in mind, we can go ahead and get a common denominator. The common denominator would be MA plus MB. So I'm going to multiply the second VA term by MA plus MB over MA plus MB. So now I'm going to get VA prime is equal to 2MA over MA plus MB, like that, and minus MA plus MB over MA plus MB. And remember that both of those terms had a VA out in front, so I'm just uh, factoring that out. Now I combine like terms and get one common denominator. The common denominator, of course, is MA plus MB, like that. But now I have 2MA minus MA. Remember, fraction bars are like groupings, they're like parentheses or square brackets or something like that. So that minus in front of the fraction has to be distributed to the MA and the MB. So I got 2MA minus MA minus MB. So 2MA minus MA is just MA, and of course all this is times VA. So I get MA minus MB over MA plus MB, and all that times VA, which again gives us yet another answer that looks like the Atwood machine. Specifically, VA prime is equal to MA minus MB over MA plus MB, and all of that times VA. And as I said, it looks like the Atwood machine. And the Atwood machine, we found that the acceleration was m2 minus m1 over m1 plus m2 times g. So you can see how it sort of looks like that. Anybody have any questions on that? So this is a fun sort of neat little problems where you just get to solve algebraic expressions and stuff like that. So I highly recommend you trying to have fun with it, and it'll only make you better whether your career is going to be in a physical science or in engineering or maybe even going into med school. There's just it's kind of rewarding, and it's overall just a good ability to think in the abstract that comes in handy. Now that we've gotten part A, now we want to consider what these answers become when MA is much bigger than MB and then the other case. So let's start with part B. Part B, we're going on the assumption that MA, the moving particle, is much larger than MB. So if you want to think about what this is like a Mack truck running into the back of a, Honda Civic or something at a stoplight. That's that's what we're talking about. So this is not a good scenario for the poor Honda Civic, but that's what we're going to work out. So first off, we're going to take VA prime, and what I'm going to do is I'm going to multiply everything by 1 over MA over 1 over MA. So 1 over MA over 1 over MA. This is just something that we've learned from years of doing this kind of stuff, that it makes it pretty easy to understand what's going on when you do this. So that's why I'm doing it, and that's still times VA. Now you can see that when the 1 over MA hits the MA, I get 1 minus and then MB over MA. And then when the 1 over MA hits the MA again, I get 1, in this case, plus MB over MA. And then all of that is times VA. But in the limit, as I'll write it like this, as MA is much, much greater than MB, MB over MA is approximately equal to zero. So what you see here is that when the initial vehicle, the big vehicle, the Mack truck is moving, let's say 60 miles per hour, and it runs into a Honda Civic or a, a Prius or something really small like that, or a Honda Fit, for instance, then you end up getting that VA prime is just going to be undeflected. In other words, the Mack truck is just going to plow right through everything and not even slow down. So if their speedometer was reading 60, it could pretty much read 60 all the way through the collision, which obviously is not good for the person in the small car, and pretty sad for the person driving the big car. Now let's look at VB prime. So again, VB prime is equal to, again, I have a 2MA over MA plus MB, so I'm going to multiply by 1 over MA over 1 over MA, but the answer is 2MA over MA plus MB times VA. So when you actually carry this out, you're going to get 2 over 1 plus MB over MA times VA. But as we know, as MA approach is much bigger than MB, then that forces the MB over MA to be zero. Therefore, VB prime is horribly 2 times VA. So if the Mack truck hits the uh, Prius, for instance, at driving 60 miles per hour, then the Prius is going to take off from that collision at 120 miles per hour. That's devastating. Okay, that's really what's bad about huge vehicles being on the road next to small vehicles. As long as everybody's driving and pay attention like they're supposed to, no problems. If someone, screws up, whether it be the small car or the big car or just a third party that just happens to screw up and makes the other cars hit, then yeah, all bets are off and bad things can happen. So just keep that in mind. That's part of the reason why so many quote unquote more wealthy people buy a lot of bigger cars because they can afford them, and then it also protects them. So, and I'm not trying to blame wealthy people. I try to do it myself, whether I'm wealthy or not, for my own daughters. Okay. All right, now we're going to do the other way around. This time we're trying to consider what happens if the target's really massive and, this little insignificant speck is running into it. This one reminds me of the story when I was out on the track at NC State and I sort of got into the zone where I was watching this dude that didn't have any legs and he was like running really fast. I was really impressed. He had those things that looked like grasshopper legs. They were prosthetics, and he was running those. And I had talked to him and asked him, how quick he could do a 100 yard or 100 meter dash and stuff like that. And he was like 12.8 seconds. So I was like, good Lord, I can't do anywhere near that. So I was paying attention to him. I'm walking across the track, and then all of a sudden, this huge, huge linebacker runs into me. He's a linebacker from NC State, and all I can think is, oh man, I'm a grown man. I'm going to hurt this poor student. So I kind of hold on to him and grab him in hopes that I won't harm him. And basically, what happens is I become a hood ornament to this big football player. in my gusto to protect him, I'm all hugging him and caressing him, making sure nothing bad happens. And I said, "You all right, man? I'm so sorry. That was my fault." He said, "Oh no, you're cool. You're cool. Don't worry about it, bud. No problem." I was like, "Okay." And I went off and I started urinating blood and I had to go to the doctor. So that's what happens when a big guy collides into what I thought was a big guy, me. But when you compare me to a middle linebacker for NC State, then yeah, I'm not so big. All right, now we're going to do the same thing. So VA prime is equal to MA minus MB over MA plus MB. But this time I'm going to multiply by 1 over MB over 1 over MB. Of course, we still have the VA over here. So in this case, we're going to get MA over MB minus 1 over MA over MB plus 1 times VA. And as MB becomes much, much greater than MA, then the MA over MB becomes zero, and we get basically Come on, get rid of that. We get that VA prime is equal to negative VA. So in other words, the Prius running into a parked Mack truck is going to bounce off the Mack truck going exactly the same speed that it was going beforehand, but in the opposite direction. So that's a pretty devastating blow again for the small car. Now we'll do VB prime. VB prime 1 over MB over 1 over MB. Oops, getting really small fitting it in there. Oops. Let me just scribble some stuff on it. That'll fix it. So 1 over MB over 1 over MB times 2MA over MA plus MB. And this thing's doing that weird thing where it starts erasing lines when I'm near the bottom. So in this case, I'm going to get 2MA over MB divided by MA over MB plus 1. And again, the limit as MB is much, much bigger than MA makes MA over MB essentially 0. So that means that this is going to give us VB prime is approximately equal to 0. So that's what happens with that one. Any questions on that? So the massive Mack truck that's sitting perfectly still, when the Prius runs into it at 60 miles per hour, if the Prius was really a hard ball instead of a Prius that's going to crumple, and the crumpling's part of the point, the crumpling saves the person because it allows the acceleration to take place over a larger distance, and therefore it's not as jolting of a force. But the Prius is going to bounce off at 60 miles per hour going backwards, but the Mack truck is not going to move at all. It's going to have a velocity of 0 after the collision. Any questions on that? All right. Your book talks about nuclear collisions, and to be honest with you, when you're dealing with subatomic particles, a lot of times the collisions happen so fast that even the attractive and repulsive molecular, or I should say molecular, the attractive and repulsive electrical forces of attraction and repulsion between the particles, sometimes they don't last long enough, and therefore no energy is stolen. So a lot of collisions at the nuclear and subatomic level are often considered to be elastic. So that's why this is a fairly realistic problem. Let's go to example 9.9. Example 9.9 says a proton P of mass 1.01 atomic unified mass units traveling with a speed of 3.60 times 10 to the fourth meters per second has an elastic head-on collision with a helium nucleus. The mass of the helium nucleus is 4.00 U initially at rest. What are the velocities of the proton and the helium nucleus after the collision? As mentioned in chapter 1, one unified atomic mass unit is 1.6605 times 10 to the negative 27th kilograms, but we won't need this fact. Assume the nuclear collision takes place in nearly empty space, so we're ignoring air resistance, that kind of stuff, okay? So what I do know is P is equal to 1.01 U, and I know that VP is equal to 3.60 times 10 to the fourth meters per second. We also know that it's running into an elastic collision head on with a helium nucleus that's at rest. So the mass of the helium nucleus is 4.00 unified atomic mass units, but the velocity of the helium initially is 0. What we want to know is VP prime equals question mark and V helium prime equals question mark. Solution. Again, we have MP VP is equal to MP VP prime plus MHE VHE prime. That's going to be equation one. But we also have VP, that would normally be minus VHE, but we don't have a VHE, that's zero, is equal to negative VP prime minus VHE prime. So that's our two equations we're going to use here. And what we can do is, again, we can substitute, for instance, we can solve for VP prime in 2 and plug that into 1. So solve 2 for VP prime and plug into 1. So VP equals negative VP prime plus V helium prime. That tells us that VP prime is going to equal V helium prime minus VP. So we have that. And now we can plug that. I'll call that equation 2 prime. So plugging 2 prime into 1, that gives us, of course, MP VP is equal to MP times VHE prime minus VP plus MHE VHE prime. So now you see you really only have one unknown, VHE. That's the whole point in doing this. I'm going to go ahead and distribute to get rid of the parentheses. That's going to give me MP VP is equal to MP. Now notice the VHE prime has a MP in one case and it has a MHE in the other, so I'm going to go ahead and factor those out. MP plus MHE times VHE prime. Now by doing that, I've taken into account this term and this term, and I've already put the MPVP, so that term's been in there. So all I really have left is minus MP VP. So I can get 2 MP VP is equal to MP plus MHE times VHE, which lo and behold, this looks a lot like the formula we just found, as it should. Specifically, V helium prime is equal to 2 times the mass of the proton divided by the mass of the proton plus the mass of the helium times the velocity of the proton initially. So I can finally calculate this. This is going to be 2 times 1.01 divided by 1.01 u plus 4.00 u. You can see that the u's cancel out everywhere. And of course, that's still times VP. So what I get is 2.02 over 5.01 times VP, and of course VP is 3.60 times 10 to the fourth meters per second, and that gives me 2.02 divided by 5.01. That's 0.403 times 3.60 times 10 to the fourth gives me 1.45, and that's technically 1.451 times 10 to the fourth meters per second equals V helium prime. Okay. Now I'm going to try to use my expression for VP prime to solve for VP prime. So using 2 prime, we get, so I'm going to say VP prime is equal to VHE prime minus VP. I don't really have to do all this algebra. I did it last time, and you saw that the answer was, but I know a number now, so I can just plug this in and I can say 1.451. I've carried an extra sig fig times 10 to the fourth meters per second minus 3.60 times 10 to the fourth meters per second. So I'm doing 1.451 times 10 to the fourth minus 3.60 times 10 to the fourth. That gives me negative 2.149 times 10 to the fourth meters per second is VP prime. And that just shows us that the lighter particle, the proton, ran into the heavier particle, the helium particle, and bounced backwards. And it had a velocity almost as big as its initial velocity, but still it did bounce backwards. So that is the way we go about solving problem example 9.9. Hopefully that worked out pretty well for you. We still got about 20 minutes left. Let's do an inelastic collision. This one's kind of neat. I think I'm going to need a whole page for it, so I'm going to go to the next page. This is example 9.10. Now, if you notice that I don't ask, does anybody have any questions on it? It's because everybody's left. So if I might instinctively just sort of work inside of my head and do the answers and stuff and not give the normal time to ask those questions because there's no one here. Okay. Example 910 is the ballistic pendulum. It says the ballistic pendulum is a device used to measure the speed of a projectile, such as a bullet. The projectile of mass lowercase m is fired into a large block of wood or other material of mass big M, which is suspended like a pendulum. Usually, big M is somewhat greater than little m. As a result of the collision, the pendulum and projectile together swing up to a maximum height h. Determine the relationship between the initial horizontal speed of the projectile v and the maximum height h. So let me draw a diagram. That's probably the best way of working this. So we'll take and consider the ceiling. And what we're going to imagine is we've got this really big block here. And that block has a big mass, big M. And we have an itty bitty bullet. It has a mass M and it has a velocity that we're just going to call V. And I really shouldn't put that V right there. I'll say the velocity here is little v. Now, what's going to happen is in 3 phases. So first off, there's going to be a collision. And that collision is going to result in this block of mass M having a bullet embedded in it. And that bullet is going to have some weird shape like that inside. And now the mass here is M plus little m. And this thing is going to take off with a velocity v1, which isn't a relevant velocity, but it's something that we'll have to get to start a little bit. Now that object has a velocity v1 and therefore has a momentum m plus big M in parentheses times v1, and then starts the third phase. The third phase is that this mass, this block, is going to swing up like a pendulum. And because of that, we're going to get a marked change in height. We might, in fact, say the change in height looks something like this. And that's going to give us a big block here And at this point, V equals 0, but the height is h. And of course, we still have the bullet embedded in it, so we still have a mass m plus m, like that. So what we're going to do is from the first scene to the second scene, we're going to use conservation of momentum to figure out what V1 is. Then we're going to use conservation of energy from scene 2 to scene 3 to figure out what the initial velocity was, since we know what V1 is. So P initial is equal to lowercase m lowercase v plus big M times 0. So that's just lowercase m times lowercase v. P final is going to be m plus m. They're stuck together now, and they're moving with a velocity v1. So P initial equals P final gives us that m v is equal to m plus m times v1, and that allows us to solve for v1. Specifically, v1 is equal to m over m plus big M times v. Now we're going to use our conservation of energy, which is ui plus ki plus work in equals u final plus k final plus work out plus e loss. In this case, we're not imagining any kind of work done against friction or compressing springs or anything like that. No work put into it by a father or compressing springs or anything like that. And in fact, we're going to have the initial kinetic energy to be, or excuse me, the initial potential energy to be 0. And then at the end, we're going to have the final kinetic energy to be 0. So that just leaves us the initial kinetic energy is equal to the final potential energy. So the initial kinetic energy is 1/2. Let me go ahead and do that in blue. The initial kinetic energy is 1/2 m plus m times v1 squared. I know what v1 is. I'm going to make use of that in a second. In fact, I'll call that equation 1. And then the u final is going to be m plus big M times G times H. So I have now equation 2, and I'm going to plug 1 into 2. And to do that, for starters, I know I can get rid of the M plus M. I want to do that in red. So this m plus m and this m plus m can cancel each other out. And I'm going to go ahead and write the 2 on the other side, and the v1 will be all that's left on the left, but that v1 is squared, so I'm going to write this as m squared over m plus m squared times v squared is equal to 2gh, because I moved the 2 over to the other side, and of course the m plus m was gone. Now I can go ahead and say that v squared is equal to m plus m over m quantity squared times 2gh. And that's what we really want, is an expression for v. So we're finally able to say that the muzzle velocity, or the velocity that the bullet had just before it hit the block, is in fact equal to m plus m over little m times the square root of 2gh. And that's the expression we were looking for. Of course, I'd normally pause here and ask anybody if they have any questions, but everybody's gone. So if you look, that is exactly the answer that your book has. Yeah, I did get rid of the squares. I just want to make sure. When I took the square root of both sides, obviously that got rid of the square of the m plus m over m. So that's why it's m plus m over m without a exponent of 2, and then times the square root of 2gh. All right, let's do the railroad car again. So this is example 912, 911. Yes. Darn it. It says railroad cars again. For the completely inelastic collision of two railroad cars that we considered in example 9.3, calculate how much of the initial kinetic energy is transformed to thermal or other forms of energy. So what we're really looking for here is what is the lost kinetic energy. So what we're looking for is kinetic energy initial minus kinetic energy final. What we found when we solved that problem was that initially the 10,000 kilogram train car was going 8 meters per second, and it ran into another 10,000 kilogram train car that was sitting at rest. That resulted in a 20,000 kilogram coupled pair of cars that are now moving at 4 meters per second. So I can calculate the initial kinetic energy as one half. And then, of course, the initial kinetic energy is just the kinetic energy of the one part of the one object. So that's the 10,000 kilograms. And that was moving at 8.0 meters per second. And of course, kinetic energy is one half mv squared. So this gives me zero point 0.5. Actually, if you turn your calculator on, it usually works a little better. So zero point 0.5 times 10,000 times 8 squared gives me 320,000, 3.20, and that's one extra sig fig times 10 to the fifth. And of course, kilogram meter squared per second squared is a Newton meter, which is a joule. So that's the initial kinetic energy. The final kinetic energy is one half of 20,000 kilograms times 4.0 meters per second squared. You can see the mass went up by a factor of two, but the velocity went down by a factor of two, and that meant the kinetic energy went down by a factor of two squared, which is four. So we actually expect about half of the kinetic energy to be missing, and you'll see that that's the result. We can go ahead and calculate this. We're going zero point 0.5 times 20,000 times 4 squared, and that's going to give me 16,000, or excuse me, 160,000. So 1.60 times 10 to the fifth joules, like that. That is a 5, not a joule. Okay. So K final minus K initial is equal to 1.60 times 10 to the fifth. There I go again with my J like 5. 1.60 times 10 to the fifth joules. And technically, that's a negative because we actually lost that much. But that's what the change in kinetic energy is. We've lost about half of the kinetic energy. In fact, it's exactly half of the kinetic energy, which is exactly what we expected because the mass went up by a factor of two, the velocity went down by a factor of two, which is what you need for momentum to be conserved because momentum is mass times velocity. So if one goes up by a factor of anything and the other one goes down by the same factor, then momentum's conserved. But kinetic energy is one half mv squared. So the mass going down by or going up by a factor of two increases the kinetic energy by a factor of two, but the velocity going down by a factor of two decreases the kinetic energy by a factor of four. So if you take and multiply by two and then divide by four, that's the same thing as multiplying by one half, and that's why we got the lost kinetic energy was one half of the original kinetic energy. All right. So now we're left with the one major problem. We actually have about 32 minutes left because it's supposed to run to 7:40, and we're going to do collisions in two and three dimensions, but more specifically, we're going to stick to two. And there is a very specific way that you can go about solving this conservation of momentum problem. And I'm going to show you that not in this first example, but in the next example, we'll work through it. We have a very straightforward way in the first example. So let's begin with, I did that in purple, didn't I? Yeah. So let's do example. Oh, well, let me go ahead and start off with the symbols and a diagram and an argument. So, you this may seem like we're handling a very specific case that's not general enough, but it is absolutely general. It turns out that you're always free to choose your coordinate system any way you want. And you can also choose any coordinate system you want. So you don't have to necessarily use the coordinate system you're in. You could, for instance, choose a coordinate system in which you're moving at, or the room is moving at 10 meters per second or something crazy like that. Because of that, we can always imagine a setup in which one particle sits perfectly still and the other particle is moving along the positive x-axis. So that's what we're doing here. We're going to say that m sub a has a velocity v sub a, and that results in a momentum p sub a, like that. And in fact, we're going to imagine that that particle is moving in the positive x direction, and it's going to run into another particle that's sitting still at the origin. That particle has a mass mb. Now, what's going to happen is specifically now, this MB might actually be sent off in this negative direction, and it's going to have a velocity VB prime right there. And that, of course, is a momentum PB as well, PB prime, say. And this would be at an angle theta B prime. And then the other particle has a velocity VA prime and a momentum PA prime, and this one's going to be at an angle theta A prime, like that. Because of that, we can use conservation of momentum to say P initial is equal to P final, like that. And then that, of course, breaks down into P initial in the x direction equals P final in the x direction, and P initial in the y direction equals P final in the y direction. And that's where we're going to go from here. So, with that in mind, I'm going to go ahead and write MA VA is equal to, now I'm going to take MA and I'm going to multiply it by VA prime, but to get the x component, I got to multiply that by cosine theta A prime plus MB times VB prime cosine theta B prime, like that. That's equation one. And that's the x component that I just did. Now the y component, because we decided the particle was initially moving in the positive x direction, that means it has no initial y component. And again, we're allowed to do that because we can set up our x-axis pointing any direction we want. So in this case, we're going to get 0 is equal to MA VA prime sine theta A prime plus MB VB prime sine theta B prime, and that's going to be equation 2. So that's our two conservation of momentum equations, and we can use those if we happen to have a conservation of kinetic energy, meaning it's elastic collision, we can add a third equation. But right now, having two equations, we can't have two unknowns, and that is exactly what example 912 is going to do. So I'm going to go ahead and solve example 912 now that we know this information. So example 912 says billiard ball collision in two dimensions. Billiard ball A moving with speed VA equals 3.0 meters per second in the positive x direction strikes an equal mass ball B initially at rest. The two balls are observed to move off at 45-degree angle to the x-axis. Ball A above the x-axis and ball B below the x-axis. What are the speeds of the two balls after the collision? So what we have is MA is equal to MB is just plain equal to M. That means we can get rid of the masses, and that'll be kind of handy. We also know that VA is 3.0 meters per second, and we know that theta A, whoa, Nelly, it just started drawing its own, neat lines by itself and made it that become the line that it thought I wanted, which I didn't. All right, so theta A prime is equal to positive 45 degrees, and theta B prime is equal to negative 45 degrees. And they want to know VA prime equals question mark and VB prime equals question mark. So all we have to do is first off, solution, since MA equals MB equals M, one is going to become VA is equal to VA prime cosine theta A prime plus VB prime cosine theta B prime. And 2 is going to become 0 is equal to VA prime sine theta A prime plus VB prime cosine theta B prime. Like that, or excuse me, that's supposed to be a sine, not cosine. Don't know. I guess I must have looked above me. That's sine theta B prime. So those are our two new equations designed for this particular problem, and all we have to do is figure out some way to calculate them. So it seems obvious here that the best thing would be plug these into equation for the y component of momentum and plug these equations in for the x component of momentum, and we should be able to get something. So if I do this, I'm going to say 3.0 meters per second, this is equation 1, is equal to VA prime times cosine 45 degrees plus VB prime times cosine negative 45 degrees. But remember, cosine is an even function, which means it's the positive half on the right-hand side of the y-axis is a mirror image of the left-hand side of the y-axis, so that cosine of 45 is equal to negative cosine of is equal to cosine of negative 45 is equal to the cosine of 45. So we can actually divide through by a common factor of cosine 45. And of course, cosine 45 would normally be 1 over the square root of 2, which we try to make it into root 2 over 2. But in this case, it's going to be in the denominator. So it's going to be 3 times the square root of 2 for the right hand or for the left hand side. So I'm going to say, therefore, 3.0 meters per second times the square root of 2 is equal to VA prime plus VB prime. So that's one equation we have. And of course, 3 times the square root of 2. The square root of 2 is about 1.414. So 1.414 times 3 would give me 4.242. 4.242 meters per second is VA prime plus VB prime. And I'm going to call this equation 3 just because, we've already used 1 and 2. Now I'm going to plug the same information into equation 2, only this time we're dealing with a sine, and sine is an odd function. So the sine of negative 45 is the negative of the sine of 45. So in this case, I'm going to get from 2, I get 0 is equal to VA prime times the sine of 45 degrees plus VB prime times the sine of negative 45 degrees. But that is equal to VA prime times 1 over the square root of 2 plus VB prime times negative 1 over the square root of 2. So there's a negative in this case. like that, because the sine of negative 45 is the negative of the sine of 45. And we got both sides equal to 0. So what we see here is VA prime minus VB prime is equal to 0. And that means that VA prime is equal to VB prime in magnitude. So that's one of our answers. And since we know VA prime plus VB prime is equal to 4.242 meters per second, and VA prime is equal to VB prime, we can say 2VA prime is equal to 4.242 meters per second, and that gives us VA prime is equal to 2.121 meters per second. And of course, VA prime is equal to VB prime. So that also means VB prime is equal to 2.121 meters per second as well. And that's it. We get the exact same answer for both of them, and that is the right answer that the book had as well. And we still got 20 minutes left, which is good because that's what the part I need to show you next. So let's go on to example 913. And in this case, we are going to include conservation of kinetic energy because it's going to be an elastic collision. And I'm going to show you how to work with that. And we do need more or less the whole page. So I'm going to say example 913, proton-proton collisions. A proton traveling with a speed of 8.2 times 10 to the fifth meters per second collides elastically with a stationary proton and a hydrogen target, as in figure 918. One of the proton, that's the same diagram that I drew at the top of the original of the previous page. One of the protons is observed to be scattered at a 60-degree angle. At what angle will the second proton be observed, and what will be the velocities of the two protons after collision? So M A is equal to MB is equal to the mass of the proton. And we see that VA is equal to 8.2 times 10 to the fifth meters per second. And one of the angles, theta A prime R theta B prime, is equal to positive 60 degrees. And what we want to know is VA prime and VB prime. Okay. You really can't tell one proton from the other, so that's part of the issue here. But we don't know which one is which. That's why they're saying that. Now, how do we go about solving this? Well, to go about solving this, I'm going to first make use of the fact of conservation of momentum. So momentum in the x direction is going to give us, since the masses are the same, I'm going to go ahead and divide that out. And what we're going to get is VA is equal to VA prime cosine theta A prime plus VB prime cosine theta B prime. And in fact, I'm going to find that that's very useful if I put all the A's on one side and all the B's on the other, in which case I get VA minus VA prime cosine theta A prime is equal to VB prime cosine theta B prime. And I'm going to actually square it a little bit later, but I just wanted to get to that part. So I'm going to call this equation 1. Now the conservation of momentum in the y direction is going to give me 0 is equal to VA prime sine theta A prime plus VB prime sine theta B prime. Again, I want all the A's on one side and all the B's on the other, so I'm going to say VA prime sine theta A prime is equal to the negative of VB prime sine theta B prime, like that, and that's going to be equation 2. And now I'm going to use conservation of kinetic energy, and that's the 1/2 ma va squared is equal to 1/2 ma va prime squared plus 1/2 mb vb prime squared. But ma is equal to mb, so I can get rid of the masses, and the 1/2 I can get rid of by multiplying by 2. So ultimately, all I have is va squared is equal to VA prime squared plus VB prime squared, like that. So that's going to be equation 3. So there's my three equations. And of course, I have three unknowns. Either I have theta A prime is unknown and theta B prime is 60, or vice versa. Then I also don't know VA prime or VB prime. So first off, I'm going to square equation 1. And when I square that, I get VA squared minus 2VA VA prime times cosine theta A prime plus VA prime squared cosine squared theta A prime. The right hand side is much easier. That's just going to be VB prime squared cosine squared theta B prime, like that. So we'll call this equation 1 prime. And now I'm going to square 2. I've already got them in the right format. And in fact, what it's going to become is VA prime squared sine squared theta A prime equals VB, oops, equals VB prime squared sine squared theta B prime, like that. And that's going to be equation 2 prime. Now, the reason I did that, you can probably see already. If I add equations 2 prime and 1 prime, if I do that, what we get is this wonderful little thing where basically I have VA squared minus 2VA VA prime cosine theta A prime plus VA prime squared times sine squared plus cosine squared. That's the whole reason that we did this, because that just makes it 1, and that gets rid of one of the square trig functions. The same thing's going to happen on the other side, and in that case, of course, it just becomes VB prime squared sine squared plus cosine squared. And I didn't even use the time to write out what the arguments of the sine and cosine were, because it's obvious that it's cosine squared plus sine squared is equal to 1. So now I have a nice new expression that says VA squared minus 2VA VA prime cosine theta A prime plus VA prime squared is equal to VP prime squared, like that. And that's going to be equation 4. Now all I have to do is I can actually use equation 3 to get rid of one of my unknowns. So for instance, I'm going to solve equation 3 for VB prime. Solving, or actually for VB prime squared, solving for VB prime squared, I'm going to get, looking at equation 3, VB prime squared is going to be equal to VA squared minus VA prime squared, like that. So this is going to be called equation 3 prime. And I'm going to plug equation 3 prime into 4. And when I do that, I get VA squared minus 2VA VA prime cosine theta A prime plus VA prime squared is equal to VA squared minus VA prime squared. So I've just substituted that. You can automatically see that the VA squared on this side is going to cancel out the VA squared on this side. And we can also see that the VA prime can come over to the left hand side from the right hand side. And when I do that, I'm now going to get 2 VA prime cosine theta A prime plus 2 VA prime squared is equal to 0. There's clearly a common factor of 2 VA prime in here. So I'm going to divide both sides by 2 VA prime to VA prime. And when I do that, I get VA cosine theta A prime plus VA prime is equal to 0. And that allows me to figure out what VA prime is. So I'm trying to make sure I didn't lose a negative or anything. Let me see. There was a negative in front of this. That's what happened. There was a negative right here, so I got to have that negative there, and that's going to fix this. So now what I have is VA prime is equal to VA cosine theta A prime. So we can go ahead and assume for a second that theta A prime is the 60 degrees, and we'll see what comes of that. So we can say VA, which is 8.2 times 10 to the fifth meters per second, times the cosine of 60 degrees, and that gives us VA prime is equal to 8.2 times 10 to the fifth times cosine 60 gives me 4.1 times 10 to the fifth meters per second is VA prime. And that seems pretty reasonable. Now what we can do is figure out what VB prime is from the VB prime that we had for equation 3 prime. So equation 3 prime implies that VB prime, looking for 3, okay, VB prime is equal to the plus or minus square root of VA squared minus VA prime squared, like that. So VB prime is going to be equal to the plus or minus square root of VA is 8.2 times 10 to the fifth meters per second. That's going to be squared minus VA prime, which is 4.10 times 10 to the fifth meters per second. That's going to be squared. And that's going to give me the plus or minus square root of now 8.2 squared minus 4.1 squared gives me square root of 50.43 times 10 to the fifth meters per second. I'm just making use of the fact that both of them had a common factor of 10 to the fifth, so I didn't have to type all that junk in. And we're going to go on with the magnitude just being a positive. So the square root of 50.43 is in fact 7.10. So now we have VB prime is equal to 7.10 times 10 to the fifth meters per second. And that's our VB prime. So now that we have that, we can plug this back into equation 2 prime, which I wrote but never circled. So plugging these into not 2 prime. I don't want to plug them into 2 prime. I want to plug them into, I guess that wouldn't be bad, but I really wanted to plug it into the original form, which is just equation 2. So I'm going to plug that into equation 2, not 2 prime. So with this in mind, I got equation 2 is VA prime, which we found was 4.10 times 10 to the fifth meters per second times the sine of theta A prime, which is sine of 60 degrees, is equal to the negative of VB prime, which is 7.10 times 10 to the fifth meters per second, times the sine of theta B. Oops, wrote cosine anyways. Sine of theta B prime. That implies theta B prime is going to be equal to, I'm taking the 4.1 divided by the 7.1, and this is going to be the inverse sine of course, the sine of 60 times 4.1 over 7.1. That's what we're taking all this for. And there's actually a negative in there. Let me just go ahead and erase it. There's actually going to be a negative in here because of the negative sign that was in the equation. So it's going to be negative 4.1. Oops. Notice the 10 to the fifth is going to cancel out anyways. That's why I'm just writing the 7.1 and the 4.1 uh, times the sine of 60 degrees. And what you're going to get is basically 4.1 divided by 7.1 gives me 0.577. I multiply that by the sine of 60, and then I multiply that by a negative, so I end up getting the inverse sine of negative zero point 0.5, and that, of course, is theta. Actually, let me write it in red so it'll show up. Theta b prime is negative 30 degrees. And that's because theta b prime turned out to be the inverse sine of negative 0.500. And that's why we got that. So now I've solved all of the conservation of momentum, conservation of kinetic energy, collision problems. This was example 913. It's the same answer that they got as well. And they give you a nice little problem solving, momentum, collision, and conservation problem solving steps. So I highly recommend you read over that to make some sense of it. That's all we can fit in. We've only got about 3 minutes left, and all we have left to do is the center of mass section of this chapter, and we will do that next time. Center of mass and center of mass translational motion. Systems of variable mass, rocket propulsion. I'm skipping that section. I think I've gotten most of them out of the homeworks and the practice tests, but I don't mind you doing those in there. So by all means, do them. Just know that you're not going to be tested on it, so you don't have to do that on an actual online test or a face-to-face test. So hopefully that works out for you. That's it. I'll wait here till the last person leaves in case anybody has any questions, but there's nobody here yet. And unless anybody shows up, that means I'm going to be gone soon. So have a good day, and I will see you next time. Bye bye. Still nobody here. And it's about 38 after, so that's good enough. See ya.